It's got it. Yeah, all right. And now I know what you mean. Okay. Okay, let's see. So the thing that I would like to do to start is my first lecture today is in many ways going to be an overview and a setup for my own subsequent lectures, which I have in mind, plus Frank's lectures, which are happening. Did I not do something? Is that okay? Maybe we should wait for the technical. Are we okay? Okay, good. So what I'm going to do is give kind of an overview, which we'll set up for my own lectures for the rest of this week. We'll also set up for Frank's lectures, and also Steve Audi. I haven't seen him here, so he'll be. These lectures this will all be kind of a really fast. This part of it will be a very fast overview of what's going to come later, and will also put me in a position to talk about a critical issue that will inform our discussion of dependent types. So that's my major theme for the week, is talking about dependent types, which perhaps some of you are interested in. But I can't assume that you all have, I don't think I should assume that you all have the background that you need in order to appreciate what's going on with the theory of dependent types. So what I want to do is I want to start out with just a bit of a crash course sort of overview of a topic called intuitionistic logic, which I'm going to broach from simultaneously from an algebraic and a proof theoretic perspective. Okay, so that's what's going to happen. So the way I like to describe this is I think of intuitionistic logic. Maybe you have or haven't heard that term before, but the way I like to half jokingly, but only half, think of it is it's logic as if people mattered. Okay, this is my view about what intuitionistic logic is all about. And the reason it's all about that, and why I present it that way, as if people matter, is because it is very much focused on the idea of the process of doing math and eventually doing computer science is a process of communication. It's all about communication of knowledge. Okay, this is what we want, is communication of knowledge. This is the basic idea. And so what I mean by this is we have the primitive notion in logic. The main thing we're interested in is expressing whether A is a proposition, and Frank is going to go into a lot of this in great detail, which says that A is sort of a sensible assertion. Let me just write A sensible here on the writing, but A is a sensible assertion. It makes sense to write this down. And then the crucial thing is A is true, which is the kind of thing that you learn in school. So an assertion is true, and what it means is that, and this is the important part where people come into it, it means I know a proof of A. So the idea is that this is just syntax for what in a textbook you write theorem, there are infinitely many primes, for example. What you are saying is, we'll call this A. Okay, let's give that a name A just to line up the notation. And when I say theorem A, it means I claim that A is true, of course, that's what it means. But if you're doing a math book, you don't get to just sort of, or in your homework or something, you don't just get to assert that something is true, or you do, but it takes a certain amount of credibility to get away with that. Because implicitly, all right, is the idea that you know a proof of it. And so invariably what comes after here, after you state theorem, is there's a proof, and there's some sort of an argument, and some sort of end of proof marker, okay, that goes on here. So that's the notion of truth. So the idea here is that something gets to be true only by virtue of your having a proof. That is the critical idea. So this is a little bit different from like what you probably learned in school a long time ago. I'm sort of guessing because it's fairly standard. Probably somewhere along the way, people taught you about truth tables. At least my experience was when I was like a young teenager. In geometry class, we spent some time learning the truth tables for all the logical connectives, and you go through all these things. And then seemingly they completely change the subject and start doing Euclidean geometry, where the emphasis is on writing a proof, and you have this sort of chart form where you would write down a deduction. And in some way, it's not really very strongly connected up. What does this story about truth tables and Booleans and bits have to do with the writing of the proof, and what is the grammar of proof? And that is a central idea. So proof theory, in some way, which we're going to talk about here, Frank is going to talk about a lot, okay? Proof theory is really talking about a formal or precise grammar of proof, you might say that. Okay? That is a notation system, if you want to say it. You can think of it as a notation system, a notation for proofs. Okay? And moreover, it's going to involve a notion of equivalence or execution of proofs, equality of proofs. And in fact, this idea of equality of proofs is where I'm going to try to get to in this lecture. It gives you a notion of when are two proofs the same. Before I get to that, and that will motivate something else, let me just mention something about grammar of proof. Probably many of you, a lot of you here, maybe it's possible that for this audience this isn't the best example, but for many people at some stage in their career have a lot of trouble understanding what is a valid proof. Okay? I know from teaching at university for quite a long time that many students have a hard time getting it. So one way to address the problem, there are many ways to address the problem, is to think of it like a kind of English composition class, and sort of proof theory is kind of the math composition class, where the idea is to, let's get the mechanics down of exactly what it is to constitute a proof. Okay? That's what's going to happen. So the idea about proof theory is to do that, to give us a formal notation for proofs. And then it will raise, and I'm going to get to this, back to this by the end of my lecture, an important issue of equality of proofs, which leads to the idea directly to the idea of an algebra of proofs. Because remember that which is this algebraic view that I was alluding to before. Because remember, in algebra, the basic idea of in algebra is you're calculating whether one expression is equal to another, maybe. So when you learn, elementary algebra in school, you learn to manipulate polynomials, for example. So you have various forms of expression, and you want to know when are they equal. Or if you look at more abstract algebraic structures, groups or something, they're given by equational laws. So you're worried about equality. Okay, you're always dealing with equality. So what is going to happen is I'll motivate this a little bit. So proof theory will give us a notation, and the algebra will give us some way of reasoning about when are two proofs equal. So the reason to do that is to give us a concept of what abstract object are we talking about. You see, because if you give some idea of just a notation for proofs, that's well and good, but then you'll find, as we'll see shortly, there are little variations you can put into a proof, and you wonder, well, which ones matter and which ones don't. And you sort of would like to quotient out by some equivalence relations, and I'll talk about various degrees of doing that, about equivalence relations, in order to isolate the abstract character of the proofs as some kind of mathematical objects. So what we wind up with at this point, which is very important to intuitionistic logic, is the idea that proofs are mathematical objects. Okay, I have to say mathematical object. I'm trying to be very emphatic here in the way I explain things. Because in the conventional story that people tell you, like the one I learned that I explained to you when I learned geometry a long time ago, you have these, Booleans. The mathematical objects in play are the Booleans and the Euclidean plane and various geometric figures. Those are the objects you play with. The proofs are just the way you talk about them. Okay? And you learn how to write those things down and how to write a convincing argument that shows that two triangles are congruent or so on and so forth. Well, that's fine as far as it goes. But the interesting thing here when you engage in proof theory and develop the algebra of proofs is that the proofs themselves become mathematical objects. Okay? They are things that have exactly the same status as every other mathematical object, as points in the plane, as functions in space, as geometric figures, as. all the proofs become mathematical objects. Now, this is not to say, for those of you, obviously you're all computer science people or have some experience in computer science, this is not to say the trivial thing that things can be quoted and used as strings because of the equivalence relation. Okay? So the idea is their proofs are mathematical objects, and I would even emphasize at the risk of being overly underlining the same point, I'll double emphasize this point. They're abstract mathematical objects, by which I mean they're characterized by an algebra. They have some kind of notion of equivalence between them, and they thereby, and then the interesting point will be that equal proofs have to be interchangeable in all contexts. So then it's a much more subtle business than just talking about something like strings. So I don't want you to get off, run off and say, oh yeah, I know all about quoting and string, because it's pretty much irrelevant. Okay? And we'll come back to that in a moment. I mean, you can do that, and I'm not disputing that, but that's not the interesting thing. That's not where the action is. Okay, so we're going to see this. So the idea of intuitionistic logic is you take the idea of a proof very, very, very seriously, much more so than any other branch of logic. And there's a payoff to this, and there are many payoffs to this, and boy, we'll spend the whole couple of weeks here drawing out the implications of this fact. But the one that I can say straight away that comes out of this is if you think about what you learned in algebra, when you learn in algebra, one of the things you get, and in fact the origin of the word, something wrong? Oh, did somebody, no? Okay, the origin of the word algebra comes from an Arabic word meaning, someone here who speaks Arabic will check me, a method of calculation. Okay, that's where it comes from. It's Al-Khwarizmi's work from, I think, like the 13th century. So it means a method of calculation. Okay, that's the idea. So originally, like most branches of math, these methods were invented basically in order to figure out ways to make money. Okay, this is the way probability was done. This was invented for this reason. Algebra was done as ways of doing calculations of measurements and so on. So it's a method of calculation, which in this case we will think of as computation. Okay, so that's an important point, is that by thinking of proofs as having an algebraic structure, that algebraic structure gives rise to a notion of calculation. That notion of calculation is a model of computation. Okay? So what we're going to have then is we're going to have a notion where proofs are programs. So this is the idea. So it's method of calculation. Proofs are mathematical projects, and in fact proofs are nothing other than programs, computer programs, things that can be executed or can be calculated with. Okay? So they're programs. There are programs, to use a jargon, to foreshadow a jargon that I'm going to use a little bit later. They're going to be programs, the jargony way of saying it is in extension or viewed extensionally, or that's the jargony way of saying it. I'll explain later what that means, or as abstract objects. So I have to, excuse me if I'm being overly emphatic, but I do have to emphasize it's not an issue about quoting. Don't get that idea, okay? So it's really treating programs as abstract mathematical objects. So that's the basic setup, okay, of what intuitionistic logic is all about, okay? And what Frank is going to be doing is talking a lot, seriously, about proof theory, and I'm going to give you a little kind of foreshadow of that because I need to set up some things for you. And what Steve Audi is going to be talking about is the algebra of proofs or category theory. And what everybody is talking about is really just computer programming. Okay? So there's this thing which I like to call the sort of Holy Trinity here of computer science. Okay? So we should keep this over the side, which is I like to call the Holy Trinity, which is the correspondences between proof theory, which is sort of the theory of logic and proofs, algebra and category theory. And then the subject in the computer science side is programs or type theory. Those are the same thing. Okay? And these all have tight correspondences. This is like what I tongue-in-cheek call the doctrine of computational Trinitarianism, which is the the computing in three persons principle, that we have that the idea of a computational concept arises as, perhaps it arises as a notion of computing, but it may also arise, the same concept may also arise in algebra, and it may also arise in logic. And in fact, I would turn that the other way around and give it a more normative force and say, you don't know what you're talking about until whatever idea you come up with, till you understand it all three ways, as a notion of computation, as a notion of proof, and as a notion of algebra or algebraic structure. If you find something that has good meaning in all three senses, you have what I would call a proper scientific discovery. Okay? At that point, you've done something which is permanent. You've really made something permanent, something that will last to eternity. You've really discovered something significant. You've got a real discovery if you discover some conception that makes sense from all 3 points of view. So the beauty of this is that the way I like to think about it is it's a way of making working on these problems in a certain way meaningful or worth doing. Personally, your opinion may certainly vary. I find nothing more dreary than trying to chase around the recent trends of some bozo at some company who is telling us that we ought to be doing some object-oriented mumbo-jumbo with something or other. Okay, this is like, I'm not interested in this. Okay, this is like completely unimportant to me. These are the vagaries of technology that come and go, and they're popular because some big company says they're popular, and then they're not because that big company goes out of business or whatever. It's a load of nonsense, right? So if you're interested in science, maybe you're not, but if you're interested in science, this is the scientific framework for talking about programming languages, and this is what we're doing. So the reason I wish to start out by talking about logic is because, well, it's an entry point. And we'll run around this circle between me, Frank, and Steve Audi. We'll run around this circle and show you all the aspects of what we're doing. Okay, so that's the plan. So that's why I think these concepts are very central to the study of programming languages. That is, and this is what I would call the real study of programming languages. Okay, this is the real stuff where we're down to like what are the fundamental principles of computation, and that's the idea of it. Okay, that's what's going on. Okay, so good. So now I want to say a few things about how this is sort of set up in order to get somewhere, to get started, so that I can say something. Where I want to end up today is saying something about the notion of equality of proofs. So in order to do this, I need to set up a little bit of machinery. So there's a few things that Frank is going to develop, and I'm going to write it over here as a chart, sort of on the proof theory side. And I need to use this to get going, and I need to do this on the algebra side. And I'm here. What I'm going to do for the purposes of making my points is I'm going to present a slightly degenerate form of what Steve Audi will be talking about. So I will be looking at a kind of limited formulation of category theory in this setting in the form of preorders. So I'm going to be looking at the structure of certain structured preorders. This is what we're going to get to, and I'll show you what I mean by that in a minute. What Steve will do is to develop this properly into the theory of categories. So the theory of categories one way of seeing it is as a substantially, to say the least, generalization of the idea of a preorder, or the other way around, a preorder is a very substantially degenerate form of category. But I'll leave Steve to talk about that in detail. Okay, so I just want to give you a flavor. So one of the elements of the correspondence is the following one, which is that I want to bring out in this chart, which is the idea of going back to what I said before, this primitive judgment of truth. I would now like to talk about, briefly, I need to talk about it here, the notion of entailment. So I want to think of this as the idea, or which is also known as logical consequence. So Frank is going to go into this in great detail, but I need to I'll give you a little foreshadow a little bit what's going on. And the idea is this. We started out with saying, well, we were interested in judging, as the terminology will go, whether a certain proposition is true. But in reality, it's not so often that you just say outright that a certain proposition is true, but rather you say that it's true under hypotheses. So what you do is you have what are variously called hypotheses, or maybe they're called assumptions, okay, or words like that. And this is your conclusion, okay? And that's a typical terminology. And the idea, as you want to say, is that essentially that A is true, given that, and now everything resides in the given that the A1 is true and various other things, AN is true. That's the basic reading of this. And this is, for those of you who are not familiar, that's called a turnstile. And it is what it is. That's what people use it. That notation goes back to Frege in the late 19th century. Okay, so this is the idea. So what we have is this idea of logical entailment. And the interesting thing that I want to point out about the logical entailment, just to draw these correspondences between, and in the middle, what I'm going to end up writing here are types. So let's put it in the middle. But in the starting point, what I'm going to do is go on the ends, and then we'll make it meet in the middle. That's my plan. Okay? So I'll just give you a flavor. Okay? So here's a flavor. So the flavor is, if you look at this structure, I want to point out a couple of things about this notion of entailment. I am hand-waving a little bit. Okay? But the reason is I'm doing an iterative deepening. So this is supposed to be like high-level intro. So all the details will emerge, but let me hand-wave a bit. Okay, so hand-waving a little bit. Given the reading that I mentioned to you before, you would expect that if you assume something is true, then it's true, okay, which is the principle of reflexivity. Okay, that would, this is the hand-wavy part, okay? So I'm hand-waving. That ought to be part of the meaning of entailment. From a sort of algebraic or order theoretic point of view, that can be read as saying A is less than or equal to A. Okay, so it's an order. In other words, we can read this thing as being a kind of less than relation, and in fact what we're going to read it as is a kind of mapping relation is what's going to happen later. So on the category theoretic side, I said I wasn't going to do this, but I'll fill it in a little bit. You have a map. For any object A, you have the identity map from A to itself. That's eventually what's going to happen. It doesn't fit on my board. From a pre-order point of view, it just says A is less than or equal to A. Another interesting fact that you get, so this might be called reflexivity. Another interesting fact is transitivity, or the lemma rule. And this tells you, there are various ways to write this down, but again, like I say, I'm giving a little overview. If B is true on the basis of A, and A is true on the basis of C, then we can conclude, and that's the way in which we write it, that, what did I do here? That B, boy, I screwed my letters up. That B is true on the basis of C, if I did that right. Okay, and if I chose my letters better, it would have looked nicer. Okay, so that's a principle, and we can read this as a principle of transitivity, right? Because what is it saying? It's saying if A is less than or equal to B, and B is less than or equal to C, so did I mess it up? Then A is less than or equal to C. What did I do wrong here? Let's do it to make it look better, okay? So I want A less than B, B less than C. Let's do it like that. I got my letters wrong. And then it will be A less than C. That way it'll work. Okay, good. So then the notation will work. Then A is less than or equal to C. And this is just the idea, if you look in a category, if you have a map from A to B, and if you have a map from B to C, then you can compose them, right? You can do G after F and get a map from A to C. That's what will be coming up in categories, okay? But here it's the principle of transitivity, okay? So already we can see some sort of familiar looking structure, okay, is emerging, all right? That's the idea. So what you see on the proof theory side, so what does this correspond to? If you think of this in terms of logical reasoning, okay, if you think of this as logical reasoning, then it corresponds to what I would call the lemma rule, right? It sort of says, I want to prove C. You're always working on the basis of some assumptions. All right, degenerately, we'll get to the degenerate cases in a little later, but let's say we're always working under assumptions, but we're trying to show C. Then what you can do is you can break it down and say, well, B is sufficient for C, and you give an argument, and then you separately prove B. Okay? So that's the lemma rule. That's what's going on here. Okay, so this is the idea of a lemma, appealing to a lemma. Okay? And so that logical principle is really can be cast algebraically as the transitivity of this preorder. Okay, so those are two examples. There are other examples I can give. Let me just check my notation. Okay, which, yes, I will do that. Give me a second here. I have to think about how I want to do that. Okay, I'll get to that in a second. All right, any questions so far? Okay. No? Any questions? No. You're all with me? You've all seen all of this before? I don't know any of you, except possibly one or two of you. It's all completely familiar? Okay. Maybe, maybe not. All right. Well, please interrupt me and ask questions as they arise. It's more fun for everyone if you jump in. Okay, so what I want to do now is, so that's the beginnings of the structure. So now I want to look at fleshing out this structure a little bit. And so let me do it by starting, I'm going to need this to remain visible. So let me throw it up there, and then I'll come back to it in a minute. Okay, so let me observe something for you. Again, I'm at the level of, very high level thing here, of just trying to give you some main ideas. Okay, so here's this like kind of hand-wavy thing. So let's look now, let's for a moment, let's switch over. What I want to do is I want to show the interplay of ideas. So let's start on the algebra side here, what I have over here for the preorder structure. So some of you may have come across the idea of a meet, okay, a meet operation, or you could call this greatest lower bound if you want. So let's just look at what that is. So first of all, in a preorder. So I say a preorder is a reflexive and transitive binary relation. So that's what we've got so far. And I want to say that a preorder has meets, okay, means if you give me two elements, they have a greatest lower bound. That's the usual definition of a meet. You can do this also with join, and I'll do that in a moment. Okay. So what is the idea of a meet? Well, the idea is that we have this binary operation that, given two elements of the order A and B, forms another element, which is written A wedge B, okay, which has the characteristic that it's a lower bound for A. It's a lower bound for B, and moreover, it's the greatest such thing. And what does that mean? That says if you have any other lower bound for A and B, then I want to know that the meet is at least that large. And it's written like that. So this is so these are the conditions of what it means to be a meet. Okay, this is the definition of a meet. So if we have binary meets, and then we can also have a trivial nullary meet. Okay, and we can let's see if how do I wish to explain that? So the nullary meet takes no things and forms an object, which is the greatest lower bound of nothing. So the nullary meet means that for any C is less than or equal to T, which is, it's usually called T or top, which is the top element of the lattice. So this is the nullary meet. This is the 0 case, right? And this is the 2 case, so this is the binary meet, okay? And the reason I bring that up is because if you have binary and nullary meets, all binary meets and nullary meets, then you have all finite meets. Okay, that's the idea. Any finite subset has a greatest lower bound. That's the idea. Okay, so now here's an interesting thing about this structure. So that structure would be called a lower semilattice. Okay, that would be the jargon, okay, for such a thing, because it has meets. If you do it around the other way, where you have joins, I'll come back to that later, you can dualize these things, then you get an upper semilattice. So this is called the lower semilattice. So what I want to do now is jump back over on the proof theory side and tell you, well, what did I say what did I mean? Like, what does that correspond to over on the proof theory side? Well, I claim what it corresponds to is the idea of conjunction of propositions. And here is the idea. Let's think about what the first thing is saying. It's saying that if A and B is true, then surely A is true. That's what it means to be a conjunction. And if A and B is true, that's our entailment, then surely B is true. And finally, and this is the important thing, if we can look at it like this, if C true entails that A is true, so A follows from C, and B also follows from C, you get two results from the same lemma, then you can get their conjunction from that same lemma. That's just transposing from this order theoretic side over into the logic side. All I did is rewrite it, okay? And this is what I have said, okay? So this is what I've done here, okay? So that's an example. Now another thing that is useful, so you can see now that there's obviously some beginnings of a correspondence between the idea of meets and conjunctions. So order theoretic ideas like greatest lower bounds transpose over to sort of logical connectives like conjunction in a logical setting. And I wanted to draw a picture somewhere. See if I can find this. There's a useful picture I can draw. I would like to leave this up here. Okay, so let's write it like that, okay? Which is the idea of a Hasa diagram. You're probably familiar with this idea. So the characteristic diagram we have is this. That says I have to think of which direction I want to draw. Okay, so if I take A and B, what we will say is A and B is less than A. You can draw it like that. A and B is less than B. So this is our less than or equal to. That's what I mean by less than or equal to. And if C, okay, is less than or equal to A, and C is less than or equal to B, then C is less than or equal to the meet, A wedge B. So this picture here that I've drawn, okay, corresponds to these three statements that I've written here. And that's an instance, if we were restricting to preorders, that's an instance of what is known as a product diagram in category theory. And Steve will go into this in a lot more detail. But so everywhere you see an arrow, you're supposed to think less than or equal to. The arrow just means it exists or it doesn't. Either it's less than or equal to or it's not, and we have this diagram. And the point is that the solid arrows are sort of universally quantified. For any two less than relations like this, there exists, that's the dashed arrow, a relation like this. That's what is being said here, okay? So this in some way corresponds to that, okay? So that's a good picture to keep in mind, and you'll use that picture a lot. Okay, so now in order to set up for talking about dependent types, I first need to talk about types. So what I want to do, now I've started to give you a little bit of a flavor. A lot of this will get developed in much more detail shortly. But what I want to do is I want to go back and now show a correspondence between these ideas and programming languages. Okay. And the idea is the following one. What I want to do is, instead of talking about, so this is a notion of entailment, or we could say, let me figure out where to write. These don't slide, that's a little inconvenient. Okay, so I have to make room. Okay, so what was I going to say? I lost my thread. Oh, yes, right. So the idea was we said A true is A has a proof. I know a proof. Okay, has a proof or is provable. There's a little worry here. Okay, Frank will make this very clear to you as he goes along, but there's a gross abuses of the word provable, okay, in computer science and branches of logic that confuse matters a lot. Okay? So here I just mean have a mathematical proof, by which what am I driving at? I do not mean has a proof in some predefined fixed sense of the word. It just means I know a proof, it's a cogent argument that any of us can understand. This is the human aspect of intuitionistic logic. It's a principle of communication, and whether something is a valid or legitimate communication, whether it works, whether I succeed in teaching you something, is a social construct. It's not defined by fixed rules. There are things that are known to work, but who knows what invention might come up. Okay, so this is what's important here. Be careful about these words. Unfortunately, then you get into crazy, inane discussions that are based on, misunderstanding the meaning of the word provable. So I know it might be a little hard to grasp at this stage of the game, but as things develop, we'll revisit the issue, and I hope Frank will amplify my point. I'm sure he knows very well what I mean. And so, but the thing I want to get at is it has existential force, meaning that it's all about there exists something. I have a proof, there exists a proof. It is provable, right? It's the able, okay? So there's some kind of existential force in this. So what I want to do is I want to just change this a little bit and talk about what it means to actually be a proof, and it's written like this, and this is where we get the correspondence to type theory. So the idea is we'll say M is a proof of A. Okay, that is the idea. So I'm going to have a notation for proof. So this is now where we get to what I was saying to you before about having a notation for proofs. That the proofs become now very, there's a sort of I'm leading you down this path, and by the time I'm through with you, the world will look rather different to you than it might have done before. And if that's true, that's good. That's the whole point. So what I'm hoping to do is to lead you down the rabbit hole, and then you will realize there's a whole other world out there, and I think you'll never look at things the same way again. Okay, so here's the idea. So M is a proof of A. So let's go back to this. So this is the idea. Oh, so another way of saying it is that M thought of as an object can be say that it is of type A. Okay, it's just a question of you can think of this program M via this idea. Let me write PGM. The program M is of type A, or M is a proof of a proposition A. It doesn't matter. You can look at it either way. It's the same thing. Okay, so that's the idea. So what does this correspond to? Well, this also goes back to algorithmy, which I'm in the wrong page. I already scrolled, so I want to go here, which is the central idea of the notion of a variable. So one of the greatest achievements of intellectual achievements of human history is inventing the idea of a variable. And so what we're going to do here is we're going to use this notion of a variable. And the idea of a variable is if I'm going to have an entailment that says something is a proof of A on the assumption that I have a proof of A. Well, if you assume that you have something, but you only know about it. I assume I have an odd prime greater than 100. I don't know what it is exactly, but I know it's an odd prime, and I know it's greater than 100. Okay? So this is what the idea of a variable is for, so a variable object. So what you do is you say, well, rather than assume A is true, I will assume that I have a proof of A. Let's give it a name, call it X. In a math book, it's usually parens 10.3, right? Okay? But we'll use a notation that is a little nicer, symbolic notation. So we'll use X, all right, which is a variable, just like you did in school, all right? And if X is assumed to be a proof of A, then it bloody well is a proof of A. And so we get this idea of the entailment, this idea that A true gives A true means that I can use a variable. And so that's the first thing. So this is the notion of variable. Now, what is the notion of a variable? Well, the notion of a variable is grossly abused in computer science. And so I'm going to insist, so this is another point in which I want to insist on being careful about our terminology, just as I was about provable. I want to insist that The idea of a variable, that thing that's called a variable in like almost any programming language that you can throw a stone at, okay, is not a variable. Okay? What is a variable is the thing you learned in school, okay? You had it right when you were like 9 years old, okay? And then somebody screwed you up, okay? And I'm just saying you were right in the first place. So let's go back to like when you were 9 years old and what is the idea of a variable. I don't know about you, but when I first learned about variables, we used little geometric figures like box plus 3 is equal to 7. What goes in the box, you know? Okay, so this is what we're doing here with variables. And this is the invention of Al-Khwarizmi. And I think also the ancient Hindu mathematicians, what is his name? Brahmagupta. Yes, am I right? Can somebody tell me? Is that right? Invented this notion of a variable. Okay? And so here's where I'm getting at, is I want to look at what this idea of transitivity is. Because what I'm getting at is the idea of plugging in. Okay? So what's going to happen here, now watch me screw my letters up again. So let's say, on the basis of an assumed but unknown proof of A, I can build a proof of B. And that's what the first line says. And on the basis of, let's call this one Y, I don't have to, but I will. On the basis of an unknown presumed proof of B, I have a proof of C. Then I want to combine these. On the basis of an unknown proof of A, I want to combine them in some way into a proof of C. And what do I do here? I plug in, if I got my letters right, what I'll call N for XM. And this is called substitution, or plugging in. For now, you'll get all of the details on this later. I sort of told you I'm waving my hands. The idea here is you're just like you did in school. You know, you have, did I mess it up? Every time I mess it up. Okay, I messed it up. M for XN, sorry. Transposing letters goes with the turf. I don't know what to tell you. Did I do it right now? Is that all right? No, I didn't. M for Y. Thanks. Okay, good, yes. I just wanted to see if you were awake. Okay, so this is the plugging in that you did in school. You have a polynomial, and one of the things, probably you enjoyed this when you were really young. Plugging in stuff and calculating is cool like hell, right? It's really fun. When you first think of algebra, you think, oh my God, that's amazing. So this is what we're doing, is we're just describing the process of plugging in. From a computer science point of view, what is the pedestrian term for this? In fact, there are Norton books written about this rule. What is it? What should it be called from a computer science point of view? Oh, boo! You better be able to tell me this. No, the notion of a variable, the idea of plugging in. What does it correspond to in sort of Norton book kind of stuff? O'Reilly books, whatever they're called. Trade books. No, I can't hear. In a way, there's no functions involved, but you're on the right track. Really? Someone? Yes, link editing. This is called I'll call this the LD rule, just to be provocative about it, or link editing. The only thing a linkage editor is doing is performing substitution with the world's most grotesque syntax. Okay? .o files are some unbelievably arcane syntax, but what they're achieving is substitution. Okay? This is what is going on. Okay? So this I call the LD rule, just for fun. Okay? Like Unix LD. Okay? That's what is being done here. It's just substitution. Okay? And notice that, again, there's this kind of correspondence. So this in the middle now is mediating, you might say, between the proof theoretic side and the order theoretic side. And we have here, or eventually the category theoretic side. And this is the type theoretic view. So here the idea is that I'm doing the most rudimentary things about what are programs. Well, variables are programs, and I can plug one into another. I still haven't given you any honest-to-God programs, all right? So what I'm going to do is give you an honest-to-God program, okay? Okay, which I will do on this chart, which I will put in here. Well, this will be, these are usually called products. or tuples, and we won't call them something else that I could call them. Okay, so let's figure out what that must look like. Okay, so we can look at this any old way we want. How about if I start here? All right, I'll start with this one. So let's look at what this means in terms of programs. It says, well, if given an x, which is of C, if you can give me an m, which is of A, I'm just like doing the thing here, right? And if you given a y, which is of C, in fact, I'm going to insist on calling it x. It's going to make my life easier if I do that. Then give me an n, which is a b. Okay. So if you have a proof of A from the lemma, if you have a proof of B from the same lemma, then on the basis of that lemma, you have a proof of A, and what's usually written cross or star or something, hash, and it depends on the language, okay, A times B. And what would that be? Well, what is the content of M and N? What is the content of this conjunction? It's the fact that they're both a proof of a conjunction ought to be two proofs, which we'll write as an ordered pair. And write it like that. And what is going on here is, if you assume a conjunction, then you can get the first conjunct by referring to it, let's say, first of x, and the second conjunct by, say, second of x, b. Oh, and then if I'm going to use a different notation, then there's a notational thing, right? There are one thing you do run into is there are established notational conventions in each independent field, and so when you're trying to make them all harmonize, you get into little creases. So it's not so common to use a wedge in a programming language, but you could. So I'll just write it as cross, okay? Because that's the more usual way of doing it. And by the same token, it would be rather weird looking to write a meet as a cross, although you perfectly well could. It's just one of those things. There are different traditions that flowed together and then crashed into each other. Okay, so we have a notation that looks like that. Okay, so that's like the basic architecture. What is my time slot? Huh? Oh, okay, good. I'm in good shape. Okay, good. Usually there's a bottle of water. Is there water somewhere? Jim, where'd Jim go? I need some water. He's gone? Okay. Okay, so what was I saying? Okay, this is illustrative of the overall architecture. Okay, so this is what we're going to do. And this is going to be very richly developed. But now I want to get to a jumping off point, okay? And the jumping off point has to do with the equational properties of these proofs, okay? So the first thing I want to get across is the overall architecture, how these parts fit together, so that we have the notion of logic or proof theory, type theory, and category theory or preorders that we're writing over here, this kind of algebraic structure. And I wanted you to see the nice correspondence. Of course, I've shown you, oh, thank you, Frank. I've shown you the neatest, most straightforward, most direct case. There's a hell of a lot more to say about that, which we'll get started on in the next lecture. But before we, so let me just skip a few things in my notes because I would like to at least set up a particular problem. Oh, okay, yes, there's two things that I would like to set up with you. Give me a moment here. I have to think about what I want to do here. Frank, you're planning to talk about negation? Okay. Okay. So, all right. So what I would like to do now is to then let me just I'll come back to that in a minute. So what I would like to do now is start talking a little bit, the beginnings, about equivalence of proofs. And this is where is the right jumping off point for me to talk about dependent types. That's why I needed this. This is partly to serve as an overview and partly to set up for what I need to talk about next. So the question I want to get at, and I'm going to begin looking at right now, is the idea, are when are two proofs equal? And let's write it like this. M is equal to N and A, which is expressing when are M and N, or just like the assertion is, are M and N express the same proof. This is what we're doing here. Okay, so we're going to have the notion of equality of proofs. So this is where we begin to get to the idea that proofs are mathematical objects. Okay, and one of the ways in which we express that idea is we talk about when two of them are equal. Okay, and what I want to set up now is the questions of equality and what is the notion of equality of proofs. This ends up being completely central to the theory of dependent types, which is why I am where I am. Okay, all right. With me so far? So what I'm going to do is I'm going to talk about, that's not the right spot, give me a moment. This is a more subtle issue than you might think. So what I want to do, let me check the terminology that I wrote down here. Ah, yes, okay, right. Okay, all right. Okay, before I do what I need to do next about equality, I need to introduce another concept, because it will help us a lot. Okay, so let's do this. So what I want to do is I want to introduce a distinction between what is called a synthetic judgment. You're going to see what the point of this in a minute is, and an analytic judgment. And we've already have an example on the board. An example on the board is when we say A is true. There's an example of what is called a synthetic judgment. This is the terminology, versus what is called an analytic judgment. And the idea is, and this goes back to this point of having existential force, the key idea is that it requires evidence, which in the case of the judgment being true is a proof, okay, in this case. In other words, to correctly assert that a theorem is true, you have to have evidence for it. You say, oh, you say it's true. Well, then show me the proof. If you don't have the proof, well, you're just talking trash, and you haven't done anything. But to correctly assert that A is true requires evidence. You have to actually look to figure out what it means as some proof that something is true. And I want to contrast that with our other judgment, which is written MA here, which is called what is called an analytic judgment. And this is generally said to be, analytic could be said to mean it's self-evident. And what do I mean by that? And this is the traditional distinction between, in this particular domain, between proof search and proof checking. Okay? To determine whether A is true, I have to search for a proof. I mean, you can think of that as a mechanical procedure if you want, but you can also think of it as suffering, you know, over your desk, trying to figure out a proof of some assertion. Okay? So there's a process of search. And there's no getting around that. That's sort of a painful thing. Whereas this is the idea of checking. Okay? Checking a proof. And if I say to you, not merely that A is true, but here's the proof, so that's the standard textbook format, is modulo syntax, M:A, that's what you get. You can compare the argument against the thing that it supposedly proves and check whether or not it's the case. Okay? So it's self-evident. In other words, it requires no further evidence, right? Nothing in addition to what is present in the judgment itself. So all the information you need is right there in front of you, and that's the information you use to do the check. Whereas here, the information you need, namely a proof, is not there in front of you. You have to find it. Okay? So that's the distinction between a synthetic and an analytic judgment. This is going to play a role in what I say about equivalence of proofs. Yeah. What's that again? The words. In this context, they were analyzed by, given by Martin Löf in a paper called what is the name of that paper? On the meanings of logical constants and the justification for the logical laws. That's one paper, and another one is called something about proof of a proposition, evidence for a judgment, something like this. I've forgotten what it's called right now. There's some papers of Martin Löf. I didn't have them in the front of my mind. We'll look them up. So there's some papers by, most of what I'm saying here is derived from Martin Löf, a Swedish mathematician, and his work is kind of derived from many sources, but I would say in particular the Dutch mathematician Brouwer, and is a very powerful influence on Martin Löf's work. In fact, you could look at Martin Löf as having really given full development of Brouwer's beginning ideas from the 1930s. Okay? Is that the answer you wanted?
That's interesting, and I also wonder whether there's what's synthetic about the first one and what's analytic about the second.
It's just the terminology that is used. Let me just say that. I mean, the terminology goes to Kant, right? And I don't know exactly. I don't know exactly the why that particular choice of words off the top of my head. Okay. But yes, the reference point for this is Martin Löf. Okay, so now in order to talk about dependent types at all, I have to talk about equivalence of proofs. So I want to talk about when are two proofs equal. And there are various notions. That's what's interesting. When are two proofs equal? And what do we mean by equality? That's another way of saying it, is what is equality proof? It's not so obvious. And it's not so obvious because, I mean, intrinsically it's not very obvious, I don't think, what the answer to this should be. And moreover, because the tradition in math has been to ignore proofs as being whatever it is we write down for some random reason, and they're not actual mathematical objects, nobody's really studied them very much. Okay? And so it's fallen to the subject of proof theory in computer science and category theory to give a full scientific study of what it means for two proofs to be the same. Okay? So what I want to do is to start out, I'm going to introduce kind of three kind of levels. And this is going to be very important by the time we get all finished, okay? By the time we're done, we'll be talking at the third level here, and I'll get to that in a minute. Okay, so the first one of which I will call is definitional equality. That's the terminology. Okay, that's just the term. And this is going to be an analytic judgment. And a lot of times people will use the notation triple bars, but to be perfectly honest, there's no real established conventions that are completely adhered to by everybody. So anything I write is always going to be a little not quite, nothing is standard. But there's kind of standard, okay? So the first thing I want to talk about is definitional equality. So we're not used to these ideas, I don't think, unless you have experience in type theory. But if you don't have experience in type theory, you're probably not used to these distinctions. So now I have to do something that I have to take my time here because it's kind of tricky and might not look so familiar to you, and you're going to run into this when you start doing mechanizations, for example, in Calc. So it's going to be worth your while. You'll agree with me, yes? It's going to be worth your while to understand what I mean here. So this idea of definitional equality, I would call this sort of baseline. And there are different ways of explaining this. And one is, you can think of it as equality of sense, if you've ever run across that terminology. As distinct with what I'm going to do next, which I will call, I had to think of a word, and there's no standard word, so I called it denotational equality. We'll come back to that in a minute, which is going, and it's going to turn out to be synthetic, and it's going to be equality of reference. This is the terminology I would like to get on the table. The distinction, this is Frege's distinction between sense and reference. Okay? So the famous example of Frege's is there's two, this is from natural, like not particularly mathematical context, is the morning star and the evening star. Both turn out to be the planet Venus, so they're not stars anyway, but they're called the morning star and the evening star. They have the same reference. They both refer to Venus, but they have a different sense. They carry a different meaning, a different information content. Okay? I don't want to give hours and hours of lectures on Frege's distinction between sense and reference, but I kind of hope you can feel, okay, that there is information content to how you pick out a number. Okay? So here's an example. I'll give you an example that I think is even more compelling. In the conventional treatments of logic, there are only two propositions in the world, true and false. Okay? So every single mathematical theorem either denotes, it refers to true or it refers to false. Okay? But obviously, so it means in particular, all true theorems are equivalent. But obviously, right? I mean, yeah, that's obviously true in a way. But there's a vast difference in information content between the fundamental theorem of arithmetic and, let's say, the fundamental theorem of calculus, which are both true. Okay? They're both complicated ways of writing down the Boolean 1. Very complicated ways of writing them down that are vastly different. But you could say, oh, well, they're all just noise. It's just like big, fat, dust storm standing for true. Well, that's the conventional story. Why? Because the conventional story completely disregards sense, because the conventional story gives no pride of place in your theory to the proof itself. Okay? As soon as you bring the proof itself into the picture, you can sense, in an informal way, that this proof and that proof are pretty different things, even though they both stand for true. Okay? That is the idea. All right, so what we're going to be doing with definitional equality is we're trying to get at this idea of equality of sense, whereas this denotational equality is going to be equality of reference. And then we're going to have an even weaker notion, which I will call equivalence, or weak equivalence, or homotopy equivalence, and we'll get to that. Okay, and this will also be a synthetic notion. And I will not say very much about that today, or I will just barely broach this subject. But by the time we get good and sophisticated in the course of these lectures, you'll be slinging this stuff around like you were born with it. Okay, so I'll show you how that all works. But let's start out with the real basics. So what do I mean by definitional equality or equality of sense? Even if I've given you that flavor, I still haven't pinned it down. I haven't defined exactly what it is. So I'll give you a little bit of example, and this is the kind of thing that Frank is going to develop in a lot of detail. And the example is going to be derived from what I have on the board here. The idea is this. It's most easy to explain. The discussion can be had on either this side or over here, but it's best to work at it. It's notationally the most convenient to work with the type theoretic notation. So that's why I've set it up the way it is now. Okay, because I want the proofs to be objects, so I've got them. Okay. So an example of this is is the composition. So the idea is, suppose I compose this rule with that rule. What does it mean to compose those two rules? It means to perform the substitution, which I have above the board here. So suppose this is my m, okay, that I have in mind. This is the overall m up here. And I'm going to plug it into the n. The n is first of x. So if I plug this term, which is a cross b, for this variable, which is a cross b, in this expression, m for y, I wrote it there, m for y n, then what do I get? Well, if I compose those two, I will get first of mn will be a proof of A, under the assumptions that this is a proof of A and this is a proof of B, right? If you work it out, right? Do you see that? If you take this rule and that rule and use the principle of substitution, which I described here, and you put those two together, you will get this compound expression, because this is, formally, this is substitute the pair mn for x in the expression first of x. And if you calculate that out by hand-wavy rules that I haven't specified, but plug it in, you'll get that, okay? So now, here's the thing. You can think of this in many different ways. One way to think of it is a principle of proof. I proved this is A and B. So I proved A and B, and then I turned right around and said, therefore A. So obviously it's a little strange, because I prove A, I prove B, and then I say, oh, and you know what? Therefore A after all. And you say, oh, you say, okay, excuse me. Okay, I can't object to that. But it's sort of a cockamamie proof. And the reason is, and let me make room here, you might as well say that this is just as equivalent to m. That is, why not just simplify that? I mean, you kind of went all the way around the barn here. You proved two things in order to extract out the first thing you proved. Well, the hell with the n. Just forget about the whole business and just simplify it to be that. And by a similar line of reasoning, you can say, well, you proved two things, and then you turned right around and pulled one out of it. So why not just prove the second thing and be done with it and don't bother with the first? And so we get this equivalence. So these two principles are kind of a starting point, okay, for talking about a notion of equality of proofs. And these are called definitional equalities, okay? Another way to think of this is that, or equality of sense. We can also think of this as, to use computer science terminology, we can think of it as symbolic execution. And this is kind of what you learned in high school algebra. Your notion of calculation involved, for example, plugging in numbers for variables and then applying the rules of arithmetic. You take x squared plus 2x plus 1, you put in 7, 7 times 7 is 49, etc., and you do the arithmetic and you get your result. So there's an execution model there. That is, when people were teaching you algebra, unfortunately they didn't, I'm pretty sure they didn't bring this out for you, but what they were doing is they were teaching you a programming language. And in fact, all programming languages, done properly, are just big-ass generalized polynomials, okay? That's what's going on here. That's the idea of it. I'm just going to generalize this idea of computing by calculation. If you do that, then you get these beautiful correspondences, okay, which go on and on and on and on. And everything is really nice. So that's the thing that sort of the whole point of the summer school. Okay, so these are two principles of proof, of definitional equivalence. What are some other principles of definitional equivalence? Well, the ones that I kind of took for granted without even saying is it ought to be an equivalence relation. So let's just write RST here. And that will be true for all of these. These are all supposed to be equivalence relations. So clearly, whatever your notion of definitional equality is, it ought to be an equivalence relation. Every proof is equal to itself, symmetrically and transitively. That makes perfect sense, okay? Plus, we can add in, these are called, the generic term for this is sort of beta-like rules. That's, you'll see why a little bit later if that notation terminology doesn't appeal to you, it will after you learn a bit more. Okay? These are the symbolic execution rules. This is symbolic execution. You can think, I don't like that word, but people use it a lot. I mean, there is no other form of execution besides some, I don't know what the hell they're talking about, but I know that people usually say that, so I'll say it, okay? All right, okay. So that's first and second. Now, the other interesting thing is you would expect it to be what is called a congruence. Congruence properties. So, for example, if M and M prime are the same proof of, let's say, a conjunction or product, then first of M and first of M prime ought to be the same proof. And similarly for second. So we would write second, and B here. We would have principles of congruence like that. And moreover, we would expect to have further principles of congruence. Like, if M is the same as M prime, and if N is the same as N prime, then the pairs Mn and M prime N prime ought to be the same. So that's did I get it right? Yeah. That ought to be the same. Okay? Those should be the same proof. So we have, these are called congruence principles. Okay? It can replace equals by equals anywhere you see it. Okay? So we should certainly have that. And now an interesting question comes up. So are you with me so far? Okay? Because without these rules, there's no obvious, don't jump to conclusions. If I didn't put these rules in specifically, there would be no reason to think that they hold. Okay? I want you to see that. If you just say, these equations hold plus it's an equivalence relation, it does not imply that you can replace equals by equals anywhere. It's an additional condition. Okay? And another way of saying it is that, this is a slogan-y way to say it, all operators respect definitional equivalence. Okay? That's an idea. Okay. So that's the meaning of these congruence rules. So first and second, as operators, respect definitional equivalence, meaning if you give them equivalent arguments, they give you equivalent results. And the same here for the pairing operator. Okay. Now I want to draw the distinction between, and then I'll finish, between definitional equality and this, what I'll call denotational equality. In order to do this, I need to wave my hands a little bit again, because it's just a question of the timing of the lecture. So everything will come out in due course, but I have to like a little bit fudge because you got to do something to get started. Okay. So here's the example that I want you to understand. This next example is of the utmost importance to everything you're going to do the rest of the time you're here, particularly with your mechanizations, and it's going to drive you crazy. Okay? So let's watch. So this example is a little out of band. It's not material I've developed yet. Okay? We'll develop the appropriate material shortly. But here is the idea. So let's say we define addition by recursion equations as follows. Somewhere else, somebody must have done this. They'll say a plus 0 is equal to a, and they'll say a plus, the successor of b is the successor of a plus b. So these are 0 and successor for generating the natural numbers. This is a very simple way of doing it. Okay, but let's just say we define addition in this manner. So this is our definition. Okay, this is how we define it. So this is the definition of addition on n, natural numbers which are generated by 0 and successor. Okay, so here's the thing that I want to show you that's important. Okay, are you with me so far? I want to distinguish equality of sense and equality of reference. So here is the idea. So first of all, if I wrote something like 2 plus 2, I claim that this should be considered to be definitionally equal to 4. Let me not write colon n every time. Let me just write it like this. It's supposed to be colon n for the natural numbers, but let me just write it like this. This is a true correct definitional equivalence. Okay? Well, because 2 means, successor of 0, right? This is the 4 times. If you apply these equations, and we treat those as definitional equivalences as stated, then you'll get this as a correct definitional equivalence. That's no problem at all. Here's where it starts to get a little sticky. For any x in n, okay, with entailment, you will also be able to show that, for example, x plus 0 is definitionally equal to x. Okay, if you want, I'll put n here, but I'll tend to drop that off. Okay? Why? Because it's the definition. X plus 0 is equal to x. Here's the definition. It says if you see this pattern, it's equivalent to that, so that's x. I deliberately chose x to be a variable here for the reason it will become apparent in the next line. However, it is not the case that if I have x in n, that 0 plus x is definitionally equivalent to x. This is not the case. You're not going to like that. Okay? And the reason is, the notion of definitional equivalence is the equivalence relation that's induced by the definitions only. It's the least congruence given by the definitions of the operators involved. So with respect to the first example, I use first and second. I define the operators by these equations, and I take the least congruence. Here, I define addition by these equations, and I take the least congruence. This will not be in that relation. Okay? The reason is, this is inductive on the right, and there's nothing you can do. This is just a variable. No definitional rule applies because x is a variable. It's not 0. It's not a successor. Okay? In order to prove, however, you might say, but wait a minute. They stand for the same thing. Oh, that's true. They have the equality of reference. They both refer to x, whatever x may be. Okay? They have the same reference, but they are not definitionally equivalent. And then there are more kind of in-betweeny kind of examples, which can be maddening. So, for example, you will be able to prove, I had a nice one written down here that looked beguiling. What did I write down? Oh, yeah. That the successor of x is definitionally equivalent to x plus 1. This is valid. Why? Because definitional equivalence is symmetric. Because it's symmetric, okay, x plus 1 means x plus successor of 0. X plus successor of 0 is successor of x plus 0, and x plus 0 is definitionally equal to x. It worked. But things that look really close to that do not work, okay, as principles of definitional equality. So, for example, the successor of x is unfortunately not definitionally equal to 1 plus x. You're not going to like that. Those are not definitionally equal. Okay? And the reason is, there are ways I can prove this to you, which I have not developed. I can prove this to you, but it is not the case. And the reason is there's no way you're going to massage this around to make one of these rules apply, because that's a variable. Okay? And even worse examples then start coming up. For example, if you give me 2 variables, x and y, you cannot expect x plus y to be definitionally equal to y plus x. It's not. The reason is, definitionally speaking, there's no way to massage this equation to make one of these rules apply and to get the equation to be there. What is missing? So from the ones that fail, this one has failed. What is missing is a principle of proof by induction. Okay? Because what proof by induction does is it says, if you have an equation involving a variable, it's sufficient to show that it holds for all the ground instances. If it holds for 0 and for 1 and for 2 and for 3 and for 4 and for 5 and for 6 and so on through all of the natural numbers, if all of those things are true, then it holds for the variable. But that's a form of evidence. And a form of evidence is exactly what you don't have for an analytic judgment. Okay? So a definitional equivalence is analytic. It has to be self-evident. Anything that requires additional evidence, like a proof by induction, is going to be synthetic. And the finest synthetic equivalence is going to be called, I'll call it denotational equivalence, or equality of reference. So it will be true, then, in the sense of equality of reference, that these are equal, but they're not definitionally equal. So then I can get rid of the x's. See? And I'm warning you that my notation, nobody's notation is standard, so I'm just using a notation at the moment that I find appealing. Okay? So those are valid equations in the sense of equality of reference. They are not valid equations in the sense of definitional equality. Okay? So that is the first point I would like to get at, and I'll consider myself to be finished. I'm going to go even further in this direction by introducing the notion of a homotopy, and we're going to get to that a little bit later. So this is higher dimensional or homotopy equivalence. And I'll get to that later. I'm not going to do that. I'm not going to do that right now. I'll get back to that. Okay.
Define the addition to be commutative. Japanese can be fault.
Is it possible to do what?
Because somehow the definitions are not commutative.
Oh, yeah, that's right.
Is it possible?
Well, the question is, at some point you have to write down a definition in a way that is clear that it's well defined. So I'm using a particular principle of definition where if I say to you, I'm defining addition by these equations, you agree with me that it's a valid definition. If you start checking in more and more conditions, okay, pretty soon it becomes unclear. Maybe you didn't define the function you wanted to. Maybe everything's equal to everything now. Maybe it's ill-defined, it has multiple values, and it becomes murky. So what I was doing is, so what will happen to you is, it's always going to be the case that there's going to be some accepted forms of definition. And then as soon as you accept those down, then you're going to run into distinctions of this flavor. In other words, there's nothing rigged or special about this example. It's quite illustrative of the thing you're going to run into over and over and over again. Okay? And it's going to be the bane of your existence when you're doing your homework. Okay? It will drive you crazy, I promise you. Okay? It's a major issue. We're not used to it. See, in conventional, like textbook math, it's all equal, equal, equal. Nobody cares about forms of equality and binary and distinctions. In a relational setting, which is what we're doing, it matters. Because one can be computed in terms of the other is different from they denote the same thing. And that matters. Like the sense, okay, matters a lot to a computer scientist. And so that's why we're in that business, okay? So from a computer science point of view, it's, okay, we're interested in the programs themselves. The proofs are mathematical objects. I care about such distinctions. I can't just gloss over them, which is the conventional thing to do. Moreover, a lot of us believe this is a better way to do math anyway, okay? But that's a bit more contentious issue, okay? But at any rate, okay, we care about these distinctions. So you'll notice that as we go through all of our work here, there's a lot of like this kind of detail work in a way, but that's what leads to the whole thing hanging together and being so satisfying. It all matters, and so it's really, I hope that you'll see that it's quite beautiful. So what I'll do is I'll pick up next time in talking about equality of reference and equality of sense. I might say a few things about homotopy equivalence, but that will come up a little. I have to develop a lot of machinery before I can really do that justice. So, but I'll give you a flavor about it. And then I will then be talking about dependent types, and so I will be diverging, okay, from this point on. But the idea of equality is central to understanding how dependent types work and what they're about. So that's why I needed to get to this in this lecture. Okay, so this is an overview of the kind of thing you'll be doing and a starting point for what I'll be doing. All right, thanks for your attention.